In this video, we're going to talk about the rare exceptions and oddities, especially notable ones that come up in our Lewis structures. These are things like NO, CO, O3, just for a small list. NO, nitric oxide, is actually fairly common. It's part of nitro pills. Our body actually releases it in our bloodstream to act as a vasodilator. It relaxes the circular muscles and kind of lowers your blood pressure. Well, if we think about 1, 2, 3, 4, I'll put 5 over there to be away from our oxygen. 1, 2, 3, 4, 5, 6. Well, we go and we pair and we say, hey, 1 and 2, and that's it. There's nothing funny I can do here. I just have a nitrogen double bond oxygen, and it has one unpaired electron. This is called a free radical. Radicals are when you have an unpaired electron on a covalent atom. This often, on certain free radicals, is quite damaging. They can break parts of your cell machinery, damage proteins and cell walls and DNA, and so the reason we have antioxidants to deal with free radicals is to suppress that damage. Nitric oxide is actually a remarkably stable free radical. It's a rare example. And so we highlight it here. Often what actually happens is a second one is nearby, and they will pair to each other, and you'll get N2O2, but that bond is not strong. It's easy to fall apart, and then it floats around for a while, free and independent. So it's just an odd exception, and the idea of free radical comes up. Now this is in opposition to things like O2 minus. O2 minus, put our extra there, bond. Well, this gives us a serious problem, because that is also a free radical. This is superoxide. Superoxide is incredibly destructive. Effectively, it can wander up to any other molecule, like say a CH4 or a fatty chain, and it can break the bond and cause that hydrogen to drift over to it and pair. The net result, however, is that you've created a new free radical. Now, if you do this to, say, carbon chains that make up part of our cell walls or our proteins or part of DNA, well, you break one chunk off and your molecule is now shattered. Whatever the remainder is missing a chunk of itself. But it, in doing so, created a new free radical that goes on to do it again to some other chain. As a result, you just start breaking everything. So in general, free radicals are bad. But there's a few rare exceptions. Superoxide, I bring up, it is particularly damaging to oxygen-breathing species. In fact, it is the vast majority of all the aging that occurs. Oxidative stress is one of the main forms of aging. It just makes things break a little bit constantly. Well, that is from breathing oxygen. We breathe dioxygen. Every once in a while, we accidentally create a little superoxide in the process of turning it into other stuff. It starts ripping up our cells, and so we have to destroy it. Antioxidants are good for this. We also have enzymes who have evolved to work as fast as physically possible. That is how much we want to get rid of superoxide. They are as fast as can be on Earth. It's called diffusion limited. The molecules have to bounce around randomly till they run into each other. And so that is the fastest anything can move through your cell, and the moment it reaches our enzyme, it wipes out superoxide. CO is dangerous for other reasons, though. It's not a free radical. If we think about carbon, and we think about oxygen, well, at first we'd pair, and, well, this is the problem. You've got carbon, and at the moment it looks like it has 2 unpaired electrons. Forming your octet is incredibly desirable if you can do it. And so what effectively happens is carbon will forcibly pair these electrons and let oxygen form another bond using its own pair. The net result is you get a triple bond to oxygen, and each atom has 1 lone pair. Problem is, if you do the formal charges, that is 1, 2, 3, 4, 5 for carbon. It wants 4, it sees 5 for -1. The oxygen, on the other hand, well, 1, 2, 3, 4, 5. It sees 5, but it wants 6. So it's +1. We have an oxygen with a positive and a carbon with a negative. But the oxygen is more electronegative. It really wants those electrons more than carbon. So this is not a good state to be in. What will happen is if you have something like iron that has some electrons around it, well, they will end up attacking a carbon, and the carbon will back bond with its own lone pair, but in doing so, it can break off one of those triple bonds. As the iron electrons come in, it pushes these off, and oxygen ends up with its lone pair back. But that means your carbon's stuck on the iron, and your hemoglobin in your blood uses iron. This is why carbon monoxide poisoning in a fire is so dangerous. As smoke is filled with a lot of carbon monoxide because it hasn't fully burned the carbon to carbon dioxide. If you don't have enough oxygen around, which house fires and the like, or poorly ventilated fires will do, you make carbon monoxide. That then gets stuck on the iron in our hemoglobin, blocking up transport sites so that we can't move as much dioxygen around our blood. So you can have a person that escapes a fire and outside breathing, and nothing's getting into them. They're not getting dioxygen into the blood. All the hemoglobin that's supposed to transport it is blocked by carbon monoxide. This is part of why you'll be given dioxygen, just pure oxygen if you come out of a fire, is the hope is that, well, you might not have as many bonding sites, but if we flood you with pure oxygen, we're more likely to ensure any of them that are available pick up that oxygen. Because usually about a quarter of your hemoglobin sites don't actually pick up oxygen. Not from the normal 20% of Earth's atmosphere. But hit them with 5 times as much, you're going to exploit as many sites as possible. Carbon monoxide will vent over time. It will break back off. And so as that happens, you can breathe it out. And so as long as you can keep a person running for a while and get them to fresh air, you will clear the carbon monoxide out over time. Ozone. O3. This is why we can live on land. Originally, when there wasn't oxygen in the Earth's atmosphere, there was basically no life on land. You had to be under the water a little bit so the ultraviolet light didn't destroy you. It was all monocellular or small. Photosynthetic life shows up, starts making some oxygen, and it takes quite a while before it gets into the atmosphere and starts filling the atmosphere. Once that happens, lightning strikes, solar effects start making some of it produce ozone. If you run a big electrical current through oxygen, you'll get ozone as it reorganizes. And so eventually we built up ozone that provided UV protection, and life could survive on land without the protection of the ocean guarding against ultraviolet. And so if it wasn't for ozone, there wouldn't be land life. Well, What is ozone? What's different about it? If we try to draw it, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Most people are inclined right away to connect 1, connect 2, and then say, hey, what about our outside edges? Let's just make a triangle. Problem is, if you have a triangle, that is a 60-degree angle. They're all the same atom, so they should all be the same bond angles to each other. What we'll discover as we get to shapes is that 109.5 is the expected angle when you have two bonds and two lone pairs. That is a significantly different angle, so much so that the triangle doesn't work. And I'll just say this for all future classes. Triangles in your geometries are bad. Your Lewis structures generally don't make triangles, not of 3 atoms. There are limited exceptions, but they tend to be very quickly broken, and oxygen definitely can't do it. Not with other oxygens. You can do it with carbon for epoxies, but that's for another day. If I can't connect those outside oxygens, well, I have unpaired electrons. What the heck am I supposed to do with them? What ends up happening, and why we need to blast oxygen with an electrical current, is we move one of the electrons. One of those central oxygen electrons gets pushed to the outside edge, which frees up one of those centers as a unpaired electron. Now, you can't break oxygen's lone pair up and keep them on oxygen. It's not sulfur. Remember, it's second row. We cannot exceed the octet on that middle oxygen. But we can move one electron away, causing a lone pair to be destroyed on the center, and having now just a unpaired electron remaining. That result is you get an oxygen single bonded to the left, double bonded to the right, and a lone pair. Thing is, I could have done this to the left. I could have done this to the right. And so we can imagine a fold-in, fold-out resonance structure where we would have had a double bond on the left, single bond on the right. If we do our formal charges, well, that's going to be a negative on the outside, and our center oxygen, 1, 2, 3, 4, 5. It's going to be positive. Ozone is a resonance structure of outside oxygens being a little bit negative and a center oxygen being positive. Well, oxygen doesn't like to be positive. So ozone's pretty reactive. As a result of these energetic states, it's pretty good at absorbing ultraviolet light. It's also very good at reacting with molecules. We actually use ozone to purify water. It takes a bit of money. You have to have cheap electricity, but it's pretty effective. You just run electricity through some oxygen from the air, bubble it into your water, and it kills bacteria and parasites, but it breaks down over time into just dioxygen again. And so by the time it reaches the home faucet, it's gone, but it'll have killed any parasites in the meantime. So here's a few interesting exceptions. The most notable extra exception is boron. Boron forms 3 bonds and can be left with just 6 electrons. Boron does not have to close its octet. But if it runs into something with a lone pair, it will kind of just move to sit on that lone pair. And so it'll force a bond to be formed there. In doing so, it becomes negative and the other thing becomes positive. Often, the other atoms with the lone pairs aren't things that are going to be positive very easily. A nitrogen, an oxygen, or fluorine don't prefer this. So this is temporary. Very quickly, boron will just break back off and float away, but for a little while it was attached. and it formed what we called an adduct. Ammonia borane is an adduct that was experimented for quite a while with, trying to do the hydrogen fuel economy for cars. If you remember back in 2005, Bush 2 tried to really push the hydrogen future for vehicles. It never went anywhere. And it's not likely to go anywhere. We don't really have a good way to store hydrogen. This was one of our best options, and it just didn't really work out. But ammonia and boron can combine in these ways, and boron can stick to other things in similar fashions. In fact, its tendency to kind of glomp on to a lone pair for a moment and cause some charges is actually really useful in reactions as a catalyst. If a molecule is stable, it doesn't tend to react, so you need to destabilize it. And so if you have something that doesn't really want to react, but you throw some boron compounds in there, you can destabilize the shape, introduce some charges, make it more reactive. So we tend to use boron as a catalyst. So here's a few examples of just neat, unexpected exceptions to our Lewis structures. The vast majority of compounds absolutely obey our Lewis structure and octet rule, but especially when you have just only a few atoms, you can run into some very curious exceptions.